So let's start with classifying that there are two types of forces. There are natural forces and contact forces. There are four known natural forces: gravity, electromagnetic, weak nuclear, and strong nuclear. We say four known because, we can't say with 100% certainty that there isn't potentially a fifth or even more. Now, what makes a natural force natural is it does not require physical contact between objects. Gravity, for example, is a natural force. It's the only one you're going to learn in the first semester. But if you jump out of an airplane, the Earth doesn't need to reach up and grab you and pull you down. That's because the Earth can exert gravity, a natural force, without physically touching you. Second semester, you will learn about electromagnetic force. It often gets broken up as the electric force and the magnetic force, but they are truthfully intertwined as one. I got this little memo here about don't mix with MA. It's not supposed to be there. Okay. So contact forces, there are a plethora of contact forces, and the name pretty much gives away what exactly it does. A contact force, by definition, is a force that requires physical contact, hence the name contact force. There are four that you're going to learn about in this unit. There's a normal force, which you'll learn about today. There's friction, which you're going to learn about next class, and there's also tension, which is caused by ropes, and spring force, which, believe it or not, is caused by springs. These four forces require physical contact. You can't feel the tension of a rope unless you are physically in contact with the rope. Same thing with springs, same thing with friction, same thing with normal. Gravity is the only natural force you'll be dealing with until second semester. All other forces require physical contact. Questions so far? Okay. So I mentioned to you that there are going to be two forces we're going to talk about today: gravity and normal. So we'll start with gravity. So the force of gravity. This is also known as weight. So the force of gravity, this is a natural force. So therefore it doesn't require contact. It changes from planet to planet. So it's not the same everywhere. It does depend on your mass. Let me see what else. Yep, okay. So the force of gravity mathematically is F subscript G, or you can use a W if you wish, because gravity is also known as weight. Whether you use F subscript G or a capital W, either way it's going to equal mg. Now this, don't confuse this with ma. So the force of gravity, like all forces, is measured in newtons, abbreviated with a capital N. Force of gravity does depend on your mass, which is measured in kilograms, and G, which for Earth is 9.81 meters per second. You are free to use 10 if you would prefer, make the math easier. But G is going to change from planet to planet. So let's take a scenario where we have Earth and the moon. So on Earth, your mass is 60 kilograms. I'm just making that number up. Some of you might be more, some of you might be less, some of you might be exactly 60. G, that's caused by planet Earth itself. It's 9.81 meters per second squared. It'll be 9.81 meters per second squared for all objects on Earth. The force of gravity is mg. So that's 60 times 9.81, which comes out to 589 newtons. That's your weight on Earth, also known as the force of gravity. Questions so far? Okay. We go to the moon, your mass is still 60. That doesn't change. Mass is a measure of amount of stuff inside of you. The G value of the moon, though, has changed. It's about 1.61. Don't quote me on that. It might be like 1.63, 1.65. And now it's 1.6 something. The force of gravity equation stays the same. It's still mg. So it'll still be 60, but instead of 9.81, you're going to use 1.61. 60 by 1.61, you get 96.6 newtons. Gravity always points down. Really simple. Any questions? Okay. All right, so my next piece for the notes is this. The normal force. So the normal force is a contact force. To be specific, it's a contact force between any two solid objects that are in physical contact with each other. This is the force that stops you from walking through walls, because if you tried to walk through the wall, you, a solid object, would hit the wall, another solid object, and a force would be exerted on the two. It's what stops you from falling through the floor. It gets the name normal because of a mathematics definition where normal actually means perpendicular. So that's a key thing as we go through examples of the normal force. The normal force is always going to be perpendicular to the surface of contact. And I'll talk about the examples shown below in just a moment. One of the annoying things you're going to find with the normal force is it has no equation. The only way you can solve it is through Newton's second law. So, for example, if you took two people, one person clearly more massive than the other, and you had them stand up on the floor and the human have a normal force between them. They're both solid objects. They're exerting the normal force. The larger, more massive human would have a bigger normal force than the smaller one. If you took those same humans and you had them lean against a wall, since the larger person has more mass to begin with, they're going to exert more force on the wall. If you took a hammer and you smashed the wall, as the hammer collides with the wall, you have normal force. Now, this is where, when I talk about normal force, I kind of describe it as a matching force. It supplies as much force as needed to prevent you from falling through the wall or falling through the floor. Now, going to that hammer and wall example, if it's a sledgehammer and you're trying to knock down the wall, when you take the hammer and you hit the wall, if that wall cannot supply the needed normal force to stop the hammer, The hammer goes through the wall breaks. If someone falls through the floor, it's because the floor was not capable of supplying enough normal force to prevent them from falling through. So the floor breaks. Our third bullet point talks about how the force is always perpendicular to the surface of contact. So we see here 1, 2, 3 examples: flat ground, a shallow ramp, and a steep ramp. Now on the flat ground, we can get away with saying the normal force equals mg. Those two forces cancel out, nothing moves. The normal force is directed perfectly vertical upwards. It's at 90 degrees between the contact surface, which is horizontal. As you get on a ramp, though, normal force no longer equals mg. In fact, more often than not, it will be less than mg. And the normal force also begins to act at an angle. It's no longer acting directly upwards. That's because it always acts perpendicular to the surface. So we see the right angle here and a right angle here. You can get even more complicated. If we took, for example, a ladder leaning against the wall, you would actually have two normal forces. The first one between the ladder and the floor, and the second one between the ladder and the wall. Any questions so far? Okay. Am I free to move onwards, or do I need to leave this screen up? All right, I'm gonna see if I can move on. So to practice these forces, we're gonna take a look at an elevator. An elevator is basically a box with some cables attached to the top. And those cables will lift the elevator upwards or cut some slack and let the elevator fall downwards. And these particular problems, which you're going to do, is you're going to solve for the normal force, or basically what a bathroom scale would read. So imagine you go onto an elevator with a bathroom scale, you stand on top, and you take a look at your weight. Your weight will not be consistent. Let's go through something incredibly boring, but necessary for the moment. Let's describe an elevator ride. So, first thing, you step onto the motionless elevator, the doors close. 2, the elevator begins to accelerate upwards. 3, the elevator has reached its cruising speed. You continue upwards at a constant velocity. 4, the elevator begins to slow down as you approach your desired floor. And 5, the elevator is or has come to a complete stop. The doors open. Hopefully, this is not new information for you. That's how an elevator works. It should be a painfully boring description of what happens on an elevator ride. Now let's talk about all 5 of these steps, what's happening with the normal force. Regardless of the situation, let's say you are that average 60-kilogram human being. Regardless of the situation, the force of gravity on you is always mg. So it is always 60, and I'm going to use 10 instead of 9.81. So 60 times 10 or 600. Now, In situations 1, 3, and 5, I'm going to say the acceleration is 0. In 1, 3, and 5, there's a force of gravity acting on you, mg, at 600 down. There's a normal force acting on you upwards. So 1, 3, 5. You're motionless, acceleration is 0. 3, you move at a constant velocity, acceleration is 0. You come to a stop, acceleration is 0. Okay? So the sum of forces equals mass times acceleration. That's Newton's second law. And we just declared that in all 3 of these situations, the acceleration is 0. The forces in question are normal, which I'll treat as positive because it's up, and gravity, or mg, which I'll treat as negative because it's down. We already solved mg was 600, so we can conclude that the normal force is also 600 for parts 1, 3, and 5. Any questions on what just happened? Okay. For 2, I got to add a piece. I want the acceleration to be 2 meters per second squared upwards. And for 4, the acceleration will be 2 meters per second squared again, but downwards. We got to add those originally. So let's figure out what's happening in 2 and 4. In scenario 2, in order to accelerate you upwards, the normal force has to be bigger than gravity. That's how you accelerate up. The sum of forces equals ma. You still get the same equation on the left. The difference is this time it does not equal 0. Don't confuse A with 9.81. It's not the same thing. Normal force would be 60. I'm sorry, normal force minus 60 by 10 is 60 by 2. So that's 600. This is 120. The normal force is 720. It's bigger than gravity. It should be bigger than gravity. You have to accelerate upwards. Question?
I have a question.
Go ahead.
Or if you were given a problem like this, would we be given the acceleration normally for like the elevator?
You would either be given the acceleration or given the normal force and solve for the acceleration.
Okay, thank you.
Yep. Now for 4, since you're slowing down but traveling up, gravity is going to have to be bigger than the normal force. before your velocity is upwards, your acceleration is downwards. That means you're slowing down. Forces don't care about velocity. Forces impact the acceleration. So mg has to be bigger than normal in order to create a downward acceleration. Now that doesn't mean gravity's gotten bigger than 600. Gravity can't change unless you eat a sandwich or go to the bathroom. So normal force minus mg is ma. This is still going to be 600. The acceleration is now -2. Negative because it's down. And you'll see the normal force is 480. It's less than gravity because you're slowing down. You have a downwards acceleration. Any questions? Okay. Let's have you go through an example. All right. We'll reverse this. You're traveling downwards on an elevator. As you approach your floor, the elevator begins to slow down by applying an acceleration of 1.5 meters per second squared upward. If your mass is 55 kilograms, what is the normal force acting on you? So I'm going to let you go through this one. Over the course of 5 minutes, I'm slowly going to add in some tips onto what's going on. Go ahead and copy this down and give it a shot. Give me another moment. This should be the equation you get that you're trying to solve. M is 55. G will use 10. A is 1.5. If you got 632.5 newtons, congratulations, you are correct. That's an awful N. There we go.